In lesson 6-1 and 6-2, we're going to talk about finding inverses and graphing them. So for part 1 of these notes, Brian and Carter, 2 BHS Algebra 1 students, were given the function y is equal to 3x minus 3 by their teacher. They were asked to create a table of values and graph the function. So I want to recreate what their work should look like using the table on the left. So I want to create a table on the left for the function y is equal to 3x minus 3. So this is for y is equal to 3x minus 3. I'm going to pick values from -3 to +3, the whole numbers. So -3, -2, -1, 0, 1, 2, and 3. And then when I plug in -3 into that equation, I'm going to get 3 times -3 gives me -9. -9 minus 3 is -12. If I plug in -2, I have 3 times -2, which is -6. -6 minus 3 is -9. If I plug in -1, I have 3 times -1. That's -3. -3 minus 3 is -6. And so I don't waste all of my precious time plugging each individual x in. I can see there's a pattern here. I always want to look for a pattern that can help save me time. I know I'm counting by 3 every time. I'm adding 3 each time. So the next number I have is going to be -6 plus 3, which is -3. And then I'll have 0, 3, and 6. All right. So that is the left table. But when Brian and Carter began entering their values into the table, they entered the values incorrectly. So they switched up their x's and their y's. Since they were too lazy to change it, they simply went ahead and graphed the coordinates as they had listed them. So we're going to use the right table to fill in what they actually wrote on their paper. So what they actually wrote on their paper was instead of -3, -12, they wrote -12, -3. Instead of -2, -9, they wrote -9, -2. And then -6, -1, -3, 0, 0, 1, 3, 2, and 6, 3. All I did was flip all of the x and y's in this table I just flipped all of the x's and y's. Now I'm going to graph these two functions. So starting with the red function, I'm going to do 0, -3. I have 1, 0. I have 2, 3. And then I'm just going to put a line through that. So use this fancy function. I'm just going to put a line through it. And then I'm going to move it onto the points because it's not on the points. Oh my god, I don't know what I'm doing. I've never used this fancy tool before, so give me a second. Alright, that looks good enough to me. And then I draw the ends of that line. And then I'm going to draw the blue line. So I have -3, 0. I have 0, 1. I have 3, 2. And then I'll connect that with a line. Oh. No, I selected this. Oops. There we go. All right. Oh, that was like really good on my first try. There we go. All right. So if I wanted to find the equation for this blue line, I know that the slope is up 1 to the right 3, so it's 1 over 3x, and then my y-intercept is 1, so I'm adding 1. The two relations that we graphed above are called inverses, and we call two things inverses of each other when the x's and y's are switched. So when x's and y's are switched. Okay. What do we notice about the graph of the function and its inverse? If we look at the graph of the function and its inverse, the first thing that I notice is both of them are lines. So they're both the same shape. They're always going to be the same shape. a function and its inverse is always going to be the same shape. And in this case, the original function was a line, so the inverse was a line. So they were both lines, the function and its inverse. We also can see that they are a reflection of each. I already drew this line in the mess up part of my video. But if you draw this line here, let me redo it. I think things won't disappear. Cool. If you draw a line on y is equal to x, you can see that those lines looked symmetrical in some way. And the line that they look symmetrical over is that line y is equal to x. So this is the line y is equal to x. Those two lines look like mirrored images of each other over that line. So another really important thing is an inverse is a reflection over the line y is equal to x. This is super important, so I'm going to highlight it. The inverses are reflections over the line y is equal to x. That looks like y is equal to y. It is y is equal to x. All right. I want to know what's the equation of the inverse of y is equal to 3x minus 3. Well, if the left table was for y is equal to 3x minus 3, I already found the equation using the y-intercept and the slope of the blue tables. So I know that it is y is equal to 1/3 x plus 1. And now I want to talk about, in part 2, really what is an inverse? What's the definition of an inverse and how do we write it? So the definition of an inverse, it just means, an inverse just reverses a relation. So an inverse reverses a relation. Inputs become outputs and vice versa. Inputs become outputs and vice versa. So an inverse just undoes whatever a function did. It's just doing the opposite. So if a function was adding 3, an inverse would be subtracting 3. It's just doing the opposite. And it just means that the inputs become the outputs and the outputs become the inputs. So if I have a comma b, that's going to become b comma a. If I have the point a, b in my original function, in the inverse it will be b comma a. The way we write an inverse, we write inverse as, it looks like f to the negative first power of x, but the way you actually say it is the inverse of f of x. That's how you write it. That's super important too, so I'm going to highlight it. And there are a couple of different ways that you can find an inverse. The first way is you can use the table form. So if you have the table form, we already did this. We already found the inverse using the table form. All we did was switch the x and y values. Just switch x and y values in the table. The other way to find an inverse is to graphically find the inverse. So if you have a graph of the original, all you have to do is reflect the original over the line y is equal to x. So you can reflect the points over the line y is equal to x. And if it's easier for you, you could just find points, probably easier to find whole number points on the original function, and then just flip the x and y values, which is the same exact thing. And then algebraically, you can find the inverse as well. So if you're given an equation, the first thing that you can do is switch your x and y. So switch x and y, and then you're going to solve for y. Get y by itself. We're going to do that with the original equation we were given, and we're going to see that we we find the function this way is the same exact one as we got here, y is equal to 1/3 x plus 1. So the reason why we're solving for y is because y is always going to be our output no matter what on a coordinate plane. Y is our output. Is always our output on a coordinate plane. And we want our output by itself. We always want our output by itself, especially if we want to write things in function form. All right, so that's also important. I'm going to highlight that as well. And then we're going to do the example with the original equation that was given to us. So we had y is equal to 3x minus 3. First thing I'm going to do, switch x and y. So I'm going to switch x and y. I'm going to switch these two. That's going to give me x is equal to 3y minus 3. Instead of y is equal to 3x minus 3, I have x is equal to 3y minus 3. And then I'm going to solve for y, get y by itself. First step to doing that, adding 3 on both sides. That gives me 3y is equal to x plus 3. And then I'm going to divide both sides by 3. And that will give me, when I do that, 1/3 x plus 1 is equal to y. This is the same thing as I have here. Same thing. And I rewrite this as the inverse of f of x is equal to 1/3 x plus 1. And that's my answer. All right, then I want to do the composition of inverse functions. So there's something special about the composition of inverse functions. So we've been given this function f of x is equal to 9 minus 3x. And the first thing that we're going to do is, in order to find the composition of the function and its inverse, is we're going to have to find what the inverse is. So I'm going to rewrite this equation using y instead of f of x. So I have a y to switch my x with. I have y is equal to 9 minus 3x. That's my original function. To find the inverse, I'm going to switch my y and my x, and I'm going to get x is equal to 9 minus 3y. From there, I'm going to subtract 9 on both sides. I want to get the y by itself because it's my output. I have now negative 3y is equal to x minus 9. I'm going to divide both sides by negative 3, and that gives me y is equal to negative 1/3 x plus 3. So this is my, I'm going to just rewrite this as, this is the inverse of f of x. It's negative 1/3 x plus 3. What I want to do is I want to start with this here is the same thing as the inverse of f of x of f of 2. If I rewrite it. So I'm plugging in f of 2 into the inverse of f of x. So I'm going to start by doing f of 2. I know f of 2 is equal to, it's just 9 minus 3 times 2, which gives me 9 minus 6, which is 3. And I'm going to plug that in to the inverse of f of x, which I know is negative 1/3 x plus 3. So I'm taking this 3, I'm plugging it in. For x, everywhere I see an x, I'm going to replace it with 3. So I have f of the inverse of f of x. Everywhere I see an x, I'm replacing it with 3. And that's going to give me, when I simplify the right-hand side, I have negative 1/3 times 3 gives me negative 1. Negative 1 plus 3 is 2. So I have, when I compose an inverse and the original function of a number, it spits out the same number. So whatever number I started with is the number that it's going to spit out. Because whatever I did in the original function, I'm undoing it in the inverse. So if I did the inverse of, if I did the inverse of f of x composed with f of 3, it would be 3. If I did it of 4, it would be 4. If I did it of 5, it would be 5. The function does some stuff to that number, and then the inverse undoes that stuff. All right, so now for part 3, we're going to do some practice with these ideas. The first question, I have a table is given to me, and I want to talk about, is it a function or not? For something to be a function, I know that for every x value, there should only be one y value. But if I look here, I have x is 3 gives me 5 for y, and x is 3 gives me 2 for y as well. So because x is equal to 3 has 2 different outputs, it's not going to be a function. X equals to 3 has 2 different outputs. It's only supposed to have one output. So no, it's not a function. But if I switch all of these values, so instead of 3, 5, I have 5, 3. Instead of 3, 2, I have 2, 3. Instead of 2, 1, I have 1, 2. Instead of 6, 8, 8, 6. And then 6, -1. Is that a function? While I'm looking, is there any x value that has 2 different y's? I have 5, 2, 1, 8, 6. I don't even have a repeating x value. So based just solely on this table, each x value has only one y value. Each x value has only one y. So I know that, yes, this is a function, which tells me that, sometimes even if you start with a function and the inverse is the same shape, that inverse might not be a function as well. For number 2, I want to find the inverse of y is equal to 2x minus 1. So the first thing I'm going to do, I'm going to solve this algebraically. I'm going to change the x's, I'm going to switch the x and y. That's going to give me x is equal to 2y minus 1. And then I'm going to solve for y, get y by itself because it's my output. So I'm going to add 1 to start on both sides. That gives me 2y, is equal to x plus 1. I'm going to get that y by itself by dividing by 2. And that gives me y is equal to 1/2 x plus 1/2. And I want to rewrite this in function form. So I have the inverse of f of x, that's what I'm writing instead of y. It's equal to 1/2 x plus 1/2. This is my inverse function. I know the domain of that. That is in y equals mx plus b form. So I know it's a line. It's an infinite line that goes on and on forever. So I know the domain is -infinity to +infinity because there's no x value that I cannot plug into that equation. There's no x value I'm not allowed to plug in. Same thing for the range. Every y value is included in a line. So -infinity to +infinity. Then I want to find the inverse of y is equal to 5x minus 3 over 2. So first thing I'm going to do is I'm going to switch, because I'm going to do this algebraically, I'm going to switch the x and the y. That gives me x is equal to 5y minus 3 divided by 2. First thing I'm going to do on both sides, I'm going to get rid of the dividing by 2. So I'm going to multiply by 2 on the right hand side to get rid of that 2 in the denominator. If I do that on the right, I do that on the left. And I have 2x is equal to 5y minus 3. Then from there, I'm going to add 3 on both sides. That gives me 5y is equal to 2x plus 3. And then finally, I'm going to divide by 5 because I want 1y by itself on the right-hand side. And that gives me y is equal to 2 over 5x. 2x divided by 5 is the same as 2 over 5x plus 3 over 5. And I want to switch this to function form. So I'm going to write the inverse of f of x. It looks like f to the negative first power of x is equal to 2 over 5x plus 3 over 5. That's my function. Again, that is in y equals mx plus b form. There's no restrictions. There was never at any point x in the denominator or an expression with x in the denominator. So there's no restrictions for what I can plug in for x. the domain and range are both all real numbers, negative infinity to positive infinity. I don't know if I have to do all of these examples. I'm going to skip these two. You can try them on your own, these two, because they're very similar to the ones I just did. And I'm going to do 6. So again, I want to compose this function and its inverse. And the first thing I need to do is find what is the inverse of f of x. So the inverse of f of x, I'm going to just rewrite this as y is equal to x minus 6, because I want a y to be able to change my x and y, switch them. Now I'm going to switch the x and the y. That gives me x is equal to y minus 6. If I add 6 on both sides, that y will be by itself, and that's what I want because y is my output. I get y is equal to x plus 6. So my inverse function is x plus 6. I'm going to start by, I want to do, this is the same thing. This is the same thing as doing, composing the inverse of f of x with f of 18. So the first thing I'm going to do is what's inside, the function that's inside, and that's the original function. So I'm going to do f of 18, which gives me 18 minus 6, which is equal to 12, because I'm doing x minus 6, which gives me 12. I'm going to take this 12 and I'm going to plug it in to my inverse function. That gives me f, the inverse of f of x, but I'm plugging in 12 instead of x, is equal to, everywhere I see an x, I'm changing it with 12. And my answer is going to be 12 plus 6, which is 18. So the answer of, I'm just rewriting this down here. If I do the inverse of f of x composed with f of x of 18, I'm going to get 18 is my answer. If I plug in 18, I'm going to get 18 out, because whatever the function originally did to 18, it subtracted 6. The inverse did the opposite. It added 6. That's what a function and its inverse is. One thing, the original function, whatever it did, the inverse undoes it. So the domain and range of this does not exist. This was supposed to be, that's not supposed to be there. All right, and then for 7, I want to find the inverse of y is equal to 2x plus 1, and I want to graph both of the relations. So y is equal to 2x plus 1. To find its inverse, algebraically, I'm going to switch the x and the y. That's going to give me x is equal to 2y plus 1. I'm going to subtract 1 on both sides to start. That gives me 2y is equal to x minus 1. And then I'm going to divide both sides by 2. And that gives me y is equal to 1/2 x minus 1/2. So the inverse of f of x is equal to 1/2 x minus 1/2. And to graph that on my graph, I know I'm going to start at negative 1/2. So I'm going to start here. And I'm going to go up 1 and to the right 2. So up 1 to the right 2 puts me here. Up 1 to the, up 1 to the right 2 puts me here. And then I have 3 points, so now I can connect those with the line. And that doesn't look good. Oops, there. Draw this. I'm gonna make those dots a little bit bigger. Doesn't really matter. So that's my inverse, and then the original is y is equal to 2x plus 1, so my y-intercept is at 1. I'm going up 2 to the right 1. Up 2 to the right 1. And then I'm going to connect those. Oops. Doesn't look amazing. Right, and then I put the ends on that. And I can see this looks symmetrical over that line, y is equal to x. If I write that line or draw that line, it looks symmetrical over that line. The function, the original function, the domain was all real numbers. It's negative infinity to positive infinity. The range as well is negative infinity to positive infinity. All x values and all y values are included, all real numbers. The inverse, if I look at the red function, the domain, again, is negative infinity to positive infinity. And the range, negative infinity to positive infinity. Now looking at number 8, we should see a pattern with our graph as well. If we look at this, what I want to do is take an absolute value function and then find its inverse graphically, and then find the domain and range. And we're going to notice something about the domain and range of a function and its inverse. So I have the original function, The original function is y is equal to x, the absolute value of x plus 3. So y is equal to the absolute value of x plus 3. I'm going to make a table. I can always make a table if I don't know what something looks like, but this one's actually really easy to graph because we know that we're just moving up 3. So we should just be moving up 3. This should be our vertex. And then our slope is 1, so we're going up 1 to the right 1, up 1 to the right 1. And then on the other side, so we don't need a table. And on the other side, instead of going up 1 to the right 1, we're going up 1 to the left 1, up 1 to the left 1. So this is our original function. Forget that table, we don't need it. And then our inverse, if we want to do the inverse of that. Actually, wait, I'm sorry. We needed the table for a reason, because it's the only way we can do the inverse. So the original function, the points I plotted are -1, 4, 0, and 3, and 1, and 4. So to find my inverse, if I want the inverse, it's not easy to write the equation for that, because I don't know how to undo absolute value signs. I have x and y, I'm just switching them from what they originally were. So I originally had -1, 4. So now my inverse is going to be 4, -1. Originally I had 0, 3. So my inverse is 3, 0. Originally I had 1, 4. So my inverse point is 4, 1. And then I just plot those points. So I have 4, -1. 3, 0. And 4, +1. Notice that this is not a function. The inverse of the absolute value is not a function. It doesn't pass that vertical line test. It intersects in 2 different places. So it's not actually a function. It's still the inverse, though. It's just not an inverse function. The original function, looking at the original function, I know the domain is -infinity to +infinity. All x values are included. That V shape goes on and on forever, to the left and to the right. So it's -infinity to +infinity. The range, the included y values, it starts at the lowest value is 3, and that's included, and it goes to +infinity. For the inverse, looking at the domain, that is not going on and on forever, to the left and to the right. It starts at 3, that's the lowest value, and that's included, and it goes to +infinity. The range is infinite, so that goes on and on. I go to -infinity and to +infinity. So the lowest number is -infinity, the highest is +infinity. And what I can see here, what I should notice, is that just like my x and y values in my table, and just like finding it algebraically, I switch my x and y's. Because my x's and y's switched, it makes sense that the domain and the range are going to switch. My domain became my range, and my range became my domain. And it makes sense because I'm switching the x and y values. So I should be switching the domain and range, since domain is all the included x values and range is all the included y values. So what do I notice about domain and range of inverses? The domain and range are opposites, reciprocals.